Okay, so welcome back, and we are in the middle of discussing this chapter, I think 6, corner method. So as I said, corner is, one of the key tools in machine learning, either in the design of practical algorithms or in the analysis of existing machine learning algorithms. And here's a quick reminder about what we discussed so far. So we define a kernel as a map, a binary function on the input space. You take two inputs and return some real number. And intuitively, I said it's a measure of the similarity between the two inputs. And to capture that intuition more precisely, instead of just thinking about so kernel is such a function, instead of thinking about just arbitrary binary function on the input, we are thinking about functions which satisfy some specific properties, which are called the positive definiteness, so-called PDS kernels. And PD means positive definite. And S means symmetry. So the condition symmetric is obvious. You say that changing two arguments doesn't change the value, which makes sense because the purpose of using K is to compare the similarity between the two. The second positive definiteness is this condition for any real Cij, where Ij is from 1 to m, K, Xi, Xj is greater than or equal to 0. So this is closely related to say the K behaves like an inner product. And in fact, what we showed last time is that if you have this PDS kernels, then there is actually, so for, I think that was theorem 6.8, which is really important. That's something called the RKHS. So really intuitively what they say is if you have a PDS kernel, okay, then there is a corresponding Hilbert space. So Hilbert space, if you are not familiar with this is just a vector space with an inner product. Okay, Hilbert space together with a function, which corresponds to the feature map that encodes every input to an element in the Hilbert space. So intuitively, this Hilbert space is a space of features such that it satisfies certain properties. One of the most important properties is we can express K as an inner product. So XX prime is inner products after embedding each input to this Hilbert space. Okay. Then later, when you do analysis, this space is called RKHS. And we constructed this space by, but in the proof of this theorem last time. But then there are a few properties which are really important, which plays an important role because this RKHS actually appears quite a lot in, if you look at machine learning paper, which uses kernels in one way or another, you will see, the use of RKHS quite often. So understanding this space a little bit is actually quite good. Another key feature is that each element in this Hilbert space is actually a function from X to the real number. not all the functions, but certain functions. And then this feature map is actually come from X. So it takes each element X and has to return a function. The function is defined by this kernel. And then finally, this H has a so-called reproducing property, which means that for every function in this Hilbert space, and for every input, I mean, the behavior of the function is completely determined by how it maps its inputs, right? But what this theorem tells us is that if you know the inner products with the features, then that also completely determines the behavior of the function. So h of x is the same as the inner product of h and this feature of x. And the feature of x by the 3, this is same as k x comma blank. So this is called reproducing property. And I mean, we proved the theorem which said that there's a Hilbert space which satisfies these 4 properties. Number 1 is the most important in some sense because that really explains K can be understood as a inner product after embedding its inputs to, or encoding its inputs to some feature space. But the other 3 also plays an important role when we use this RKHS. I mean, maybe not in this course, but later when you look at some literatures in machine learning. Okay, so then at the end of the last lecture, I think Ron asked me, okay, are there any other Hilbert space that satisfy this number 1? And the answer is yes. I mean, there are really a lot of Hilbert space which satisfy number 1. So then you may ask, what is so special about this RKHS we constructed in the proof of the theorem 6.8? Okay. Color. So one possible question is, what is so special about this? Of course, number 2, 3, 4 talk about its specialty, but I mean, can you have some another insight about what's really going on? So that's one question we can ask. Now, another question is, now we talk about this PDS kernel. Is there any systematic way to generate the PDS kernel? PDS kernels. And especially, we have, I mean, by this RKHS, I mean, kernel is, in a sense, closely related to the idea of feature map. Okay, so we are really expressing some encoding of input to via this feature map. I mean, which comes with this kernel. So in the proof of theorem 6.8. Okay, so we want to have some whenever we talk about systematic way to construct PDS kernels, we want to have an understanding that what's really going on in terms of feature. Are we really, if we somehow add 2 kernels or combine 2 kernels, what we are really doing with respect to the features associated with these kernels. So that is some understanding we want to gain when we study the systematic construction for PDS kernels. So that's what we're gonna do. And so let's start with the question answer for this first. Actually, before doing so, let me just say one more words. So then, the plan for today. Is to get an answer to these 2 questions, number 1 and 2. But in doing so, we also want to answer the following question. I said the last time, I gave you one representative example of kernel, which is called RBF kernel. So x and x prime, some point in the Euclidean space. And then the kernel is defined by something looks almost like the probability density of Gaussian distribution or normal distribution. We take a distance between x and x prime and square it and divide it appropriately and take exponentiation. I said this is a PDS kernel. And then you may ask, okay, the first, is it really PDS kernel? Can we somehow prove it? So that's one question we can ask. The second question is, okay, so we are able to prove this is a PDS kernel. But if you want to use this RBS, RBF kernel, then we want to have some understanding about what kind of feature space we are really using here. Okay, so what's really going on? Of course, in practice, if you use RBF kernel, maybe you can find some solution of your problem. But if you want to have a better understanding, or improve your approach, you need to have some deeper insight about what's really going on. So one way to gain the insight is what's going to be the feature space that's associated with this PDS kernel. So at least, maybe not formally, but have some reasonable understanding about the feature space may help you to see what's really going on here. So this is the other thing that we're going to do. Okay, so let's start with the different characterization of the RKHS. Call it so it's, whether I don't know if it's the right word, but characterization of the RKHS associated to PDSK. So by, the universal characterization, something that if you are familiar, I don't know how many of you actually took courses in math, but if you take course on maybe algebra or category theory, then there's some constructions and then universal characterization, which really come from so-called adjoint in the category theory. So there's that kind of characterization, which give an idea that what you are doing or what you are building is a very canonical things in some sense. So to give this canonical construction, but to give a motivation, but to tell you about why this actually matters, think about the point x and x prime, the real line, and think about one very easy definition of a kernel, which is just take an inner product. Which is just a multiplication of x and x prime. It's a one-dimensional vector, so it's an x and x prime. Yeah. So I said this K is actually a kernel, and then associated RKHS is going to be the just real. It's going to be a function space, but you can prove it's isomorphic to the real. But there is another way to express this K in terms of the feature map followed by the inner products. The other approach is think about V prime, which maps real number to point in two-dimensional space, but all these points will lie in the x-axis. So how it's defined? It's going to be x, 0. Okay. So then you now take an inner products. After the embedding, you have x prime of x prime. Then that's going to be, the x0 x prime and 0. So it's the same as x and x prime. In other words, that's the same as k of x and x prime. Okay? So there is another description about this. Okay, so we have one way of expressing corner as an inner product over the reals, so the feature map just is an identity map. Another approach, which now is using the R square, but it's in a sense not using the plane. It's only using x axis in the plane. Okay, so then you may think, okay, then actually this R and R square, okay, what's really going on? So in the first approach, it's really, if you look at the second approach is we are having the entire real line, the entire two-dimensional plane. But what we are using is only the x-axis. Okay, so that's the only thing that we are using there. And actually what we are using x-axis, that is exactly isomorphic to the real that we are doing in the first. So what happens is that you can express the corners as an inner product in some space, but the theorem that I'm going to show you later tells us that you may use a big space. So this is some Hilbert space at H prime, and you are expressing inner products. Okay. There's an original space X, and there is a feature map, and you are expressing inner products using this Hilbert space H prime, just like an R square here. But what the theorem tells us is actually any of such representation, there always exists some subspace or subset, and the subset is essentially the same as RKHS that we are building. So this is what that we build, and then all the inner products, the encoding of a corner is really happening in this in this subset. So in these regions, even when you use this P prime, even though when you use this P prime and H prime, the inner product, the P prime maps every element in this X to here, to this subset, and then all the inner product is really happening in the RKHS. So H prime may have a junk, may have something extra, just like all these points in two-dimensional space. But when we think about where, in which place of H prime, we are really embed input to represent the input as features and taking the inner product. That's some subspace which is isomorphic to RKHS. Okay. So RKHS is some, in a sense, core which only contains something absolutely necessary. It doesn't have any junk at all, any extra bit at all. So that's what this second theorem tells us. So this, which you can also prove, tells me, I'm gonna upload the notes. The note describe some sketch of the construction here. This is say the following: if K is PDS corner, and then suppose that there also exists some Hilbert space. And feature map. This is a map to function from input to H prime such that the corner can be expressed as first compute features, and then take its inner product in H prime. It's true for all X and X prime. So then, the conclusion of the theorem is saying that if H prime like this, H prime can be used to encode this kernel, so then this H prime should contain RKHS. And then RKHS should be the place where all this encoding of the kernel happens. Okay, so that's what this tells us. This say there exists a unique linear inner product preserving. So function psi from H, which is an RKHS to H prime. So this means that Hilbert space, its structures are constant multiplication, addition, and the inner product. So this psi is preserving all the structure. But there is always unique such map, such that it's the following diagram commutes. So what's the diagram? Diagram is given X from X, and there's H prime, there's H. Then there are two ways of going H prime. The first is just using feature map V prime. The second is that we use feature map V to encode X in the RKHS, then map it by psi, which said they uniquely exist. And then the commutativity say, if you first do phi, choose yellow. If you first do phi and then psi, so we have one way to get a map from X to H prime. That is the same as the other. They're just directly going from X to H prime by this phi prime. Okay, so these two maps are, becomes the same thing. This definition doesn't tell us. Okay, if you work out this definition, the consequence of this theorem, then that theorem, what this theorem really tells us is the canonicity of the RKHS in the sense that I described in number 1, I think. Whenever there's an encoding of kernel in the Hilbert space, the Hilbert space essentially should contain isomorphic copy of RKHS, and that should be the place where all the encoding and the inner products is happening. Okay. So from this viewpoint, one thing you can see is I said if we define so I said if we define K like here, so then you can see this is really taking the inner products in the one-dimensional space. Okay, and then this one-dimensional space doesn't have any junk. This entire space is exploited when we do compute this inner product. So by this theorem, you can see that although the construction of RKHS was very complex, if you simplify it, then you can essentially show this RKHS is isomorphic to the set of reals. Okay, so the theorem is a theoretical interest and gives some justification about RKHS, but at the same time, sometimes help you to compute RKHS or guess at what RKHS actually look like. The guess what RKHS actually look like. Okay, So now let's move to the next topic. So what we're gonna do, look at now from maybe in the next 45 minutes are various constructions on PDS kernels. Then, as I said, they eventually help us to see why RBF or Gaussian kernels is going to satisfy the PDS, the positive definiteness and symmetry. And at the same time, it will also help us to see what kind of feature space is involved. I mean, feature map is involved in the definition of this, this RBF kernel. So the first construction we're going to look at is something called normalization. So what normalization is doing is say that suppose we have some input space. Suppose we have this input space, and then suppose we have a kernel K. And this kernel is PDS. Okay. So then now here's one way to construct a kernel, new kernel K prime. The K prime is defined like this. Define K prime and X and X prime. As follows, we do case analysis if K of XX is 0 or K of X prime and X prime is 0. In that case, we just map it to 0. Okay. But otherwise, which means that K of XX is not 0. And also K of X prime is not equal to 0. In that case, we normalize K by dividing it with square root of K of XX times K of X prime and X prime. Okay. So then we can show, I mean, this is called normalization. Okay. This K prime. And it's called normalization that I wrote here. Sorry about this. So then why it's called, so, and we can show, I mean that, but what's really going on here? So one way to see what's really happening is to think about RKHS related to K. So if you, this, we have a K, so let's call this H to be RKHS. Of K. So then, I mean, as I said, the K prime is also going to be a PDS kernel. So that means there has to be an embedding, so some encoding of the, I mean, there's some feature map associated with the K prime. Okay. So if you look at this RKHS of original K, not K prime, but original K, we can understand actually what's happening. So then this RKHS has a feature map V, which maps X to K of X blank. If we have this map, then we can show the K prime x and x prime is defined like this. It's really there's either 0, but this condition is really saying this map x to the here RKHS space, and then measure its size. The size is defined by square root of its own inner product. The usual thing. If the size is 0, which means that this IP, actually, I did not like this. I think the bit better definition is, if this guy is 0 in this Hilbert space, or x prime is 0 in this Hilbert space, then we're gonna map it to 0, return 0. Otherwise, what we do is we compute its inner products, but after normalizing it with by its size. Here, x prime, like this. So you can easily show the k prime, this equality is true by just using the property of RKHS and the definition of k prime. You can easily show that this equality is true. But what this equality really suggests is that actually what's going on in k prime is just change the feature map. Okay, originally we have a feature map that maps input space element in the input space is x to RKHS. But we are not using exactly the same Hilbert space. I mean, well, to understand this k prime, but we are using different map called phi prime. So what phi prime does is that if some inputs get mapped to 0 by this the original feature map, like this, and then if this is 0, then we don't change in the phi prime. But otherwise, so what we are doing is that we are, I mean, my picture is a bit misleading, but what we are doing is in space H, we are thinking about sphere. So every element of the distance 1, this doesn't like a circle, but it's a circle with 0 in the center. So if the originally some point is mapped to 0, we just map it. Otherwise, for every other things, we map them to some point in the circle by taking the normalization. Okay. So that's what's going on in the k prime. So what's good about this? One good thing, if you ignore this is 0, and what's good about this normalization is that, I mean, if you remember the notion of inner products over the circle, so if in the two-dimensional space, if you have a circle, then if you have two elements, then if you take inner products, then that's same as the cosine of this angle. So in some sense, it makes sure that usually the inner products consider two factors. One is the size of each vector, and the other is an angle. And then if you take this normalization, it forgets the information about the size so that we can focus purely on the angle, which is in some sense the relationship between the two inputs. So this normalizations let us focus on this relationship between two inputs without being distracted by by the sizes of their encoding. Okay. So just to sum up, the normalization definition is simple, but what's going on in terms of feature is that we change the feature map so that in terms of the new feature map, all the elements will be either mapped to 0 or points in the sphere. So when you use a K prime, we are really only measuring the angles between two elements in this new space. And by the theorem that I just explained to you in the RKHS, the universality theorem, this for phi prime, if you compute this RKHS, that RKHS will be some subspace. Let's use this. And maybe some subspace, maybe not, maybe same as H or maybe different from H, but it's going to be a subspace of H. That's going to be the new RKHS associated with this phi prime. And that the subspace will definitely include this sphere. Okay. I think maybe it's the same as H, but I didn't have a proof. But anyhow, so that's the normalization. So it let us, in the original kernels, which uses the features, it forgets the size in some sense of each features, and then by putting all those, the outcome of the feature representation of input, we map all those feature representation to be in sphere so that we can forget about the size and focus purely on when we compute the inner product, we can focus purely on the relationship captured by the angles between elements. So then what are the examples? Then here's an example. We have a exponential kernel or RBF kernels, say prime F that is defined as differentiation of 2 sigma square x minus x prime square minus. But if you unpack this is the square term, that can be written as exponentiation of minus 2 sigma square xx minus 2 sigma square x prime and x prime plus sigma square x and x prime. Just simple expansion. And then this expansion, if you write this, be written like this: exponentiation of sigma square x and x prime divided by square roots of exponentiation of sigma square xx and exponentiation of sigma square x prime and x prime. So what this means is, if we can show this guy is a PDS kernels, then this RBF is just a normalization of this exponentiations of this take inner product first, divide by sigma square, and then take exponentiation. If that is a kernel, so then RBF is a normalization of that kernel. Okay. And in fact, what I highlighted here is going to be the kernel. And we will show it by using the construction that I'm going to explain next. I mean, not next, but something right after. Okay. So what is the second construction? So second construction is it's a bit different flavor, but let me just change the order, okay? The second construction is there are multiple things that we're going to talk about. Some products, tensor products, and the pointwise limit, Then the last bit is power series. So what are these? So let's start with the sum and product. So suppose we have a kernel K and K prime. Both of them are defined on X, and they are positive definite symmetric kernels. Okay, and then the definition of sum and products are, as you expect, if you have I will write it like this. This is a new kernel obtained by summing operation. So if we plug in x and x prime, you have to return a real number. How it compute? What it compute is k of x plus k of x prime. Products k times k prime x and x prime. It also, what it compute is just take the product. So let's start with these two. Okay. So now, these are the, if you define like this is a kernel. It's a binary function on the input space that return a real number. But are they going to be positive definite symmetry? So symmetry is obvious by the definition. And I was what I'm talking about here. So we have x and x prime plus k prime x and x prime. K of x and x prime times k prime of x and x prime. So are they going to be a positive definite symmetry? And the answer is yes. Okay. And then they, prove, maybe the proving the positive PDS for the first is quite easy. Proving the positive definiteness for the second multiplicative product case is not so obvious. So maybe I will talk about this later. But before doing so, let me try to understand what's really going on in terms of features. So it's only for special case, but they will give a good understanding about what's really happening. So suppose that the RKHS for K and K prime are finite dimensional. So suppose they are equivalent to the to Rn and Rn prime. So what this means is for feature map for K is going to be a map from X to Rn. And then if you map this and take an inner product, you get the kernel K. Suppose for K prime. So let me be more concrete. Any n is okay, but let's just do it 2 for K prime. Suppose it is 3. So and I can't quite use this. So we have a phi prime that maps X to R3. So then we may ask, okay, what's going to be the feature map for K? We have a K prime. So what is going to be the feature map phi double prime? It's going to be X to something. And then for multiple products, that's the same thing. What is going to be the feature map phi triple prime? So it's also going to be a map from X to something. So what are these? And the answer for the first is, I thought thinking about this feature map is quite useful. The answer for the first is we are just kind of concatenating feature map for K and K prime. So we are just putting these two feature map together. So if you have a K phi double prime, it is just phi of X, comma phi prime of X prime, the X. So what this means is double prime is going to be a map that take X to R, because the phi of X, the two-dimensional, the phi prime is the three-dimensional. We add their dimension together, so 2 plus 3, which is 5. Okay. Now, like this. So 2 plus 3. On the other hand, for the second case, so it's R5. Second case is actually R6. And it's defined a bit more complicated way. Phi triple prime of X is that now phi has a two component there because it's two-dimensional vector, and the phi of X is a two vector in the two dimension. We have a first, second component. Phi prime is a vector in the three dimensions, so it has the three components. And the feature for phi triple prime is obtained this way. Phi of X, X, the first component, and then the phi prime of X and first component. And the phi of X first component, phi prime of X and second component, and phi of X, again, the first component, phi prime of X and the third component, and so on. And then the last bit is going to be phi of X, the second component, phi of prime of X, the third component. So the first one, I mean, they are both operate from the perspective of features. They operate about on how to combine features. But the summation are, in a sense, encouraging less interaction between feature of K and features from the K prime. On the other hand, these products make them interact by taking the products. Okay, so that, I mean, so if you use the combined kernel by the addition and multiplication, really in one case we are, the first addition case, we are combining features in a bit less interactive way. Product case, we are combining them in a more kind of, I mean, interacting way, okay, by taking the products like this. Okay. Now, I think for the proof, I mean, there is one theorem, part of the theorem in the textbook, say that both K plus K prime and K times K prime are PDS. So it's a theorem in the textbook. And as I said, the symmetry is obvious, and then and also showing positive definiteness for plus is easy, but showing positive definiteness for multiplication involves a little bit. So we're gonna only do this. So we will show positive definiteness of K times K prime. Okay, but so to do so, what we do is we pick the C1 up to Cm, which are all real number, and x1 to xm, they are all element in X. And what we have to show, so what we need to show, NTS means we need to show that the summation of Ci, Cj, Aj equal to 1 to m, K times K prime, Xi, Xj is greater than or equal to 0. So that's what we need to show. Let's unpack this a little bit. We need a bit more space. Unpack this a little bit. So then now we unpack the definition of a K and K prime. So then the definition tells us K of xi, xj, K prime times xi, xj. You have to show this is greater than or equal to 0. Okay, so that's what we need to prove. Okay, let's highlight this. The question is how we can prove this. Right. So that to prove this, we define first some a matrix K. So we are, really using the eigenvalues and the computation of the, the matrix based on the eigenvalues. So we define the matrix K using this the first kernel K, and this is the n by n matrix, and it's defined by this kernel. So its ij entry is going to be small k applied to xi and xj. Then last time when I explained to you about the positive definiteness and symmetry property of K, I said that's the same thing as saying this matrix K is going to be symmetric as it is going to have symmetric and have non-negative eigenvalue. Real eigenvalues. So what does this mean? This means that I explained this to you also, the K has a orthonormal matrix, which consists of its columns are eigenvectors, but orthonormal means U and U transpose. If you multiply them, then that's going to be identity. And then there is a diagonal matrix sigma, and then U transpose, it has this form. And this is a diagonal matrix with non-negative entries. Then U and U transpose, they are orthonormal matrix. So if you do so, then here's just something that you can do. Okay. So, you can say right. So then we can define the right. So we can define the K half almost the same as K, except for all the diagonal entries in sigma, we take its square root. Transpose. So for diagonal entries, this is again diagonal matrix, but it's diagonal entry for I, same as square root of sigma II. This is possible because the diagonals of sigma are real and non-negative, so you can take the square root. If you do so, then what happens is that k square is a symmetric, and the square root of k times square root of k. That's the same as taking the transpose here, because it's a symmetric, it's the same as k. If you really compute based on this definition, if you do the matrix multiplication, you can show this equality. So these two properties are true. Okay. So now we're gonna use these two properties. So we go back to what we have to prove, which is this term. So then we map it to this term here and rephrase it in terms of this matrix K. So let's just use red. So if you use matrix K, that's going to be Ij from 1 to M, Ci, Cj, and Kij. That's by definition. So if you definition of Kij, that's small k applied to xi, xj, and k prime, xi, and xj. Now the Kij, that's because of this equality, we can express Kij like this. Just sum of, because it's a matrix multiplication, it's a ij of this, the left-hand side of this equality. And so this means ij L is equal to 1 to M K half IL. And we are using symmetry of, right? We are using symmetry of K half. Okay, let's just write it directly. I think it's okay. So K like this, and it's K half and J L. Okay, so we just use the equality that I wrote here. So now using this characterizations, if you plug in, replace the Kij with a term that I just wrote, and then move this summation outside of the summation that were originally up here. Then here's what we get. It becomes sum of L to M, sum of Ij, M, Ci, K of IL times Cj, K of JL times K prime of Xi and Xj. So at this point, one thing you can notice is, this is summation. It's really the kind of summation that appears when we talk about positive definiteness of K prime. And by positive definiteness of K prime, this part is greater than or equal to 0. And if you take a sum of non-negative numbers, that will be also greater than or equal to 0. So that will show, that will let us conclude the proof. Right? So it's a bit involved, but what it does is that it uses these characterizations in terms of the positive definiteness in terms of the eigenvalues and so on to re-express the things that we want to express here. Okay. So to sum up, what we have is we have a sum and products, and they are positive. They preserve the sum on kernels, products on kernels preserve positive definiteness. Okay. Now for next. So we have something easy, which are tensor products. So now if you suppose we have a K, this one also very much like a product, but it's a bit different. So we have a kernel on X, but suppose we have a different input space where we have a kernel K prime. So both are PDS kernel. So then what tensor product does, it defines a kernel on x times x prime. So just write it like this. So it's a bit like we are constructing, and the inputs are constructed compositionally, and then each of the component we have a kernel, and this led us to define the kernels on this, the composed input. And the definition is quite what you expected, what you can expect. We have x1 and x2, then also x1 prime and x2 prime. So x1, x1 prime are coming from the first input space, and the x2, x2 prime are coming from the second input space. So in that case, we define this to be k of x1, x1 prime times k of x2 and x2 prime. Okay. And this is, again, PDS kernel. And then to show this, you just need to do a little bit of a trick, but then if you just use what the fact that the products of two kernels preserve the positive definiteness, then you can show this is a PDS kernel. And I think the more important bit is that now from the perspective of the features, then you can try to see, okay, what's really going on. Then we have a feature map P that maps some x to R and 1. Just like before, let's use R2. And feature map P prime that maps not x, but x prime to R3. So then the new feature map defined by corresponding to this tensor, let's write it like this, maps pair, which are x and x prime, to R to the 6. And its definition is very much like the products that I showed you. Okay, how it's defined, given x1 and x2. It maps the first guy is v of x1, its first component. I think maybe I just write it like this: I v of x2 j, where I is either 1 or 2, so it's, and then j is either 1, 2, 3. So we just, this is better. No, 2, j is 1, 2, 3. So that's how features construct. Very much like how the features get constructed for the product, except that here, we are not working, this v and v prime are not working on the same component of the input, they are working on the different component of the input. No, when we write it like this, no, x1, I think I used the notations maybe not quite right. So the x and x1 prime, they are on x. So these two guys are on x. So that's why we can apply k. K is defined only on x. And then for x2 and x2 prime, they are in the x prime. So I should have used the prime, then the 1 and 2 in a bit more consistent way. But I hope color really help you. Also, I made another mistake. This has to be prime. So it's a k prime. Okay, so that's the tensor products. And then there are two other things we're going to talk about are limits, pointwise limit, and power series. Let's talk about them separately, pointwise limit. So to talk about pointwise limit, what we assume is that we have a sequence of commas, Kn, on square to r for n. And then suppose that for every x and x prime, assume that limit exists and goes to infinity, Kn prime. That exists. Okay, so it's just some real number. So then we can define to be also all of these are positive definiteness metric. We can define k prime by taking the limit. And x and x prime. Then it turns out this also become a PDS comma. And so maybe enough time. So showing, I mean, this is a PDS funnel, which is quite easy to show. That's because for any the typical condition and the positive definiteness condition, what we have is that for this is some ij through m ci cj k n xi. This converge to ij m ci cj k xi xj as n goes to the infinity. But this, the left-hand side is because positive, the definiteness, the left-hand side is always greater than 0. So the right-hand side is should also be greater than 0. So if you have a sequence with every element in the sequence is greater than 0, then its limit also has to be greater than 0, greater than equal to 0. So that's why it satisfies this positive definiteness property. In terms of features, what's happening is if Kn, so imagine the case where for each Kn, essentially the RKHS corresponding to Kn is suppose that it's Rn. So or maybe some it's maybe R2n, but something that's increasing with respect to n. So then if you take a limit, we are really, this is provide one way to use an infinite dimension of feature space, because each Kn is using even though each Kn is using finite dimension of feature space, we start to use Kn. It's really we are using the limits of the feature space, which is often infinite dimensional. Now the last bit, so construction we're going to talk about is a power series. Suppose that we have a power series. So n is equal to 1 to k and xn. And then suppose that each of these an is greater than equal to 0. And this power series may converge or diverge depending on x, but suppose that it converges when x is minus rho and rho converges. So if that's the case, and so suppose we have a PDS kernel, but interesting bit is that kxx prime, because we are using x both confusing, within this range of convergence, but sometimes called radius of convergence. If that's the case, then taking this power series. It's not k, it's infinity. So this power series, a n k, this is so define it. It's fine. Like this, it's well defined because the k always falls into the radius of convergence. And also you can show that this is a positive, preserve positive definiteness and symmetry. Again, the symmetry is easy. For positive definiteness, one way to see why that is the case is when we are really taking, this is almost like a polynomial. The products of k, and then we are taking the sum, and then infinity is just taking the limit. So we already showed the products taking the summation of the kernels, taking their limits, they all preserve positive definiteness. So that's why this is a positive definiteness symmetry. So the formal proof appears in the, I think my formal argument is essentially what I just told you, but you can also find it in the textbook as well as the note that I will post during the weekend. Now they give me like 2 minutes, then I will finish off. So now we look at the construction like a sum, product, tensor product, pointwise limit, and power series. Now let's use all of these to show that RBF kernel is PDS. Now where should we start? Suppose we have x and x prime. They are in n-dimensional space. Then we start with something very easy, which is start with the first kernel is going to be just take their inner product. You can show this satisfies all the property. The properties of the inner product implies it's positive, semi-definite, symmetric, and so on. Now, after doing this, what we do use is that we now use the power series, the construction that I just told you. So now we are doing it. We are constructing this K1 in terms of exponentiations minus sigma squared. But if you do the Taylor expansion of this exponentiation function, it's going to be look like this. It's not minus, it's just plus. So its Taylor expansion is like this. We have n factorial, and then the sigma square of n, and x times x prime is k0 here. So k of x0 and x and x prime, power of n. So this is really the power series construction that I told you. Here's a nth power, and then here's the constant term that get applied, the an that applied, and we are taking their infinite sum. Okay. So because the Taylor expansion of the exponential converges for every real number, this is a well-defined kernel. So this is satisfied the PDS. Then the last bit is what I told you. If you normalize K1, that gives us the RBF kernel. Now, just to go through what's really going on in terms of features. So here we are using just standard features of the input. I said the product is a particular way of combining the features by taking their all the combinations, and then this sum is taking their limits, and So these products really allows us to think about any monomials involving the products of each part of x and x, each part of the input x. So any monomial of the degree related to n, and by taking the sum, we are really removing their limits on the upper bound on the degree of the monomial. So any monomial on x is going to participate in the construction of the features involved here. And then the last normalization part will do the normalize and move all these infinite dimensional vectors into the sphere. Okay, sorry about going over long, and that's it for today. And thank you very much.